Hey everybody, tonight we have what I would call a challenging factoring problem, and I'm just writing down something for that has to be a necessary condition. Notice the product here: 2, 3, 4 times 5 is 120, and then you have minus 24, this naked looking constant over here, equals to 96. Whatever we get, we'll have to have necessarily, it'll be a necessary condition, have a constant of 96. Now, one thing I like about this problem is that at first glance, it looks like it's factored. Look, this is the product of four linear factors on the left-hand side, but the presence of this single constant term means it's not factored. So as factored as it looks, it's a long ways from being completely factored. So let's move along. Okay, now, this very first step is even kind of hard to see, but it was for me at least, but if you pair up these two linear factors, if you take their product, you actually get this right here. Okay, and if you multiply the two inner linear factors, you get this product. And you got something working here because at least you have c squared plus 7c present in both cases. All right, now the part here that's kind of not so easy to recognize right here is that notice these two factors are separated by a constant term of 2. And so you can see 11's in the middle. So you can take advantage of symmetry here, whatever you want to call that. And this part right here would be in the form A, meaning this entire piece, we'll call it A, minus 1, right? And then here's A again, but we have A plus 1, right? And so, of course, when you take that product, you get something easier, I guess you'd call it, simpler. You get a squared minus 1, right? Okay, and you'll see that come in as we scroll down here. And that's exactly what we have right here. This is a squared. This object right here would function as a squared right up here from the structure. A squared minus 1 here is a squared. And then technically I should say minus 1 squared just to make sure the structure is evident. And it's superfluous to put the 2 there, but I'm just wanting you to know this is the difference of two squares. This is the difference of two squares. And so what we can do right here, and also another thing that's important here, I won't write this entire piece right here is minus 25, right? But minus 25 is equal to minus 5 squared. Okay, so what we're getting, we're gonna unpack it now. Okay, so what I'll do here is write this as c squared plus 7c, and now I'm going to add the square root of 20 or 5 to 11, and you'll get 16, excuse me. So you see we're going in reverse order here. This would be your a plus b form right here, and this would be your a minus b form. C squared plus 7c. And then 11 minus 5 is 6. See there, folks? See, the distance between these two numbers is 10. 2 times 5 is 10, right? Now, so this is looking pretty good right here. This doesn't appear to be something you can factor. If you just take a look at the discriminant, you would have b squared, which is 49 minus 64, which is actually complex. You would have imaginary solutions. So this is irreducible. What about this guy? This one looks like it does factor. So let's get busy doing that. C squared plus 7c. We're just recopying this because it does not factor. But this guy right here admits a factorization of c plus 1 times c plus 6. Okay, like that. Okay. Now, what did we say earlier, folks? Notice right here, 16 times 1 times 6 is 96, right? And so that, as we saw earlier, and that's not the answer. This part is the answer, but the 96, this is the answer to the question. We completely factored our original expression. And you can multiply it out to verify, but notice the product of the constant terms here is 96, just like we had 96 up here, right? 96 was the constant term for this polynomial, and so necessarily 96 would have to be the constant term for the factored polynomial. That's a necessary but not a sufficient condition. So we may have still made a mistake somewhere in here, but if you expand this out, you'll indeed see that it's equal to our original expression. So again, folks, this is the big, this is the answer right here. So anyway, that's all for tonight. Talk to you soon.